Hey everyone, welcome to the Cohere Labs Computer Vision session on. Let me quickly try to find uh, Kumar Ashutosh. LLMs can see and hear without any training. Um, let's give a brief introduction about what Cohere Labs is and what it brings to the computer vision community. So we are a small group, and it's a hybrid research lab and an open research community dedicated to contributing the fundamental research in machine learning. And like we work to solve some of the machine's most field's most challenging problems and create more points of entry into the machine learning research. And we have like 3,500 open science community members, 130 countries representing, and virtual events, 425 virtual events, and 13 plus distinct community-led programs. And we regularly do community-led events in subfields like LLMs, computer visions, reinforcement learning, NLP, and more. And we have a Roots to Research where we give uh, candid conversations about everything in pursuing this field, and where we aim to spark new ideas, inspire research connections, and more. And we are a worldwide group of researchers, and there are currently 9 subfield groups. So one has been included, and there are a couple of more programs in the works too. 2 regional groups and professional development groups that are associated. And we are welcoming Kumar Ashutosh today, a PhD student at UT Austin. And uh, he is a fourth year CS Ph.D. student at UT Austin, collaborating with Professor Kristen Grauman and a visiting Meta AI, and he researches computer vision and machine learning with a focus of video understanding and video language models. Uh, Before UT Austin, he spent 5 years in IIT Bombay, earning a dual degree in electrical engineering. And his master thesis is focused on 3D reconstruction from multi-view images. So without further ado, uh, please take the stage, Kumar.
Hi, hello everyone. Let me share my screen. Screen visible?
Yep, it is.
Yeah, okay. Hello, welcome to my talk. Feel free to stop if you have any clarifying questions, and we can
Mhm.
stop at the end for high-level questions and the overall idea-related questions.
Mhm.
So yeah, let's begin with the title of the paper is LLMs can see and hear without any training. It is to appear in ICML 2025, and this was done in collaboration with folks from GenAI Meta. Just a little bit about me. I'm a PhD student at UT Austin. My research interests include computer vision and video understanding. And see my website for more publication or other related work in this domain. So yeah, let's get started. Multimodal LLMs are powerful models. They obtain clear. Oh, by the way, I'm not able to see hands. So if there's any question, you can feel free to stop me and
Yep,
ask.
sure.
Yeah. Yeah. So multimodal LLMs are powerful models. They obtain performance far exceeding previous models, and they enable new applications. These models are being used to caption images, generate images, caption descriptions, maybe read what's in the image, do math, as we see in the last row, and so on. The issue is, although these models are very powerful, the issue is that they require large scale and or high quality data. For example, Lava uses Coco Caption, InternVL uses these data sets, Large-scale training often involves pre-training, fine-tuning, or some sort of RL feedback. For example, Llama 3 vision model initializes from a metaclip model. All these models are trained on billions of image caption pairs, and these are fine-tuned on millions of high-quality image caption pairs. So overall, a lot of effort goes into training each of these individual models. If you want a model for image captioning, we need to train a model for that. If you need a model for video captioning, we need to train a model for that, and so on for every individual task. So the question we ask is, do LLMs need this training for multimodal capabilities, or does it already have capabilities that we can exploit? The answer is no. Pure text-only LLMs can do multimodal tasks without any additional task-specific training. So in this work, we handle multiple different tasks: image, video, or audio captioning. We show improved image generation. We do even style transfer, where you have an input image, a reference style image, and then the output image transforms the input image as per the style input. And also cross-modal arithmetic, where we can add uh, multiple modalities together, like if there's a stop sign and a tree, and then the audio is of a growling thunder, then the image would try to capture both of these things together. So these are this is a wide range of tasks that we can do just by using LLMs. We do not train any multimodal LLM for this task. So the overall idea of this work is that there is a generator that generates a candidate set, and then we have a scorer that scores how good the generations are with respect to the test samples. And then it sorts the set according to score. And then finally, we use those score as a guiding mechanism to generate more sets. And then we keep repeating this cycle till we have convergence or for a predefined number of steps. And then we get the final output. We call our method multimodal iterative LLM solver. So as an example, if we use Llama 3.18 billion as the generator, and we use clip as a scorer, so what this enables is we use the generator to generate plausible image captions, and then we have like K captions. So to begin with, we have an initial set, and then we generate captions. So the caption can be anything. It is at the first stage, it just tries to guess what can be a caption. So it can be about the cat in this image, or it can be about any other animal, or it can be about anything. And then the scorer tries to match how good is the similarity between this sample and the caption. So naturally, anything that talks about grass or cat or anything that is visible in this image will have a high score. So in the scored candidate set, those captions will have higher score. And then we feed it back again to the generator, and then we again generate candidate set. So now the set will more and more go towards what is happening in this image. It is a cat and sitting on a grass. So any caption that kind of resembles that will have higher score. And if we keep repeating this process, at the end we will obtain a clean caption for this image. And this enables image captioning. We see multiple images here. The third image here is a cluttered desk with a large monitor and a window. And this has been obtained by iteration, as we discussed. So this is the first image captioning task. The interesting part about our method is you can just plug and play different scorers and generators to achieve different results. So for example, now if you replace clip with something like video clip, then we can even caption videos. So now what happens is the generator generates plausible video captions, and then the VI clip model does the same scoring for videos. So this enables video captioning. So you can see that the captions are very detailed. It is not like very generic. And this is the result of those iterations. First, we have maybe some generic captions, and that is iteratively refined. And similarly, we can replace video clip with image bind. So image bind is a method that can that projects multiple modalities into the same dimension. So we can use image bind now to even caption audio. Everything remains the same. We just replace clip with image bind, and now we can caption audios. So the birds are chirping and tweeting in a garden with variety of bird species, and this is captured in the audio as well. So far we saw using this iterative LLM feedback, we are able to do image captioning, video captioning, and audio captioning. And the good thing is it's not only limited to recognition, it can be even extended to other tasks. So in this example, what we do is um, we replace the model with a text to image flux model. So right now, what in this example, what we do is we have a text, and then we generate image using that. The generator generates image, and then we have a model pick score. So pick score rates how likely is that image, what is the score of that image, and how likely it is to be liked by humans. So pick score correlates how well humans would like an image. So we want to generate images that humans would like better. So we use exactly the same principle. In the generator, we input an image, and then the generator generates multiple images, and then we use a pick score to find which image has the highest score. Or rather, we don't generate multiple images, but we use this as a prompt rewriter. So the generator is Llama 3.18 billion, and then we generate multiple different captions, and then which is kind of like prompt rewriting, and then we give it to the candidate generation set, and then we score the generated image with pick score to find how likely is a human will a human like this image, and then we give it again back to the generator by using these scores. So this is slightly different than recognition task. This is we are using the same idea to enhance image generation using prompt rewrites. So we are able to do this, and this example shows how this improvement looks like. So the first step or the initial prompt is a red car and a white sheep. This is pretty plain, and the generated image, even though it's faithful or it correctly represents what the text wants, it is not very good looking or nice. So then what we do is we follow the same iterative process, and we do prompt rewriting. So we progressively add more detail, like a white sheep and a red car in a stunning natural landscape with few mountains and a lake. And any other, the generation is better, and then it becomes even better. A red car and a white sheep in a stunning natural landscape with a few mountains and a few wildflowers and a serene lake. So this is very descriptive, and hence the generation is liked by humans more than the initial generation.
So, Kumar, I have a question. These are
Yeah.
all using diffusion model, right, for generation?
Yes.
Okay. Yeah.
Yeah. They use the same generation model. So we don't claim any improvement on the generation model side. We just say using the same exact generation model, we can now generate better images by giving better prompts.
Okay.
Yeah. Okay, yeah. So this is how the improvement looks like over steps. Um, yeah. So now what we can do is we can even we can do we can do a lot of bunch of cool, interesting tasks. The only requirement overall is it has to have a language model based generator and a scorer that can score how good the generations are in the corresponding set. So I'll finally show like two other examples. First is style transfer, where what we do is we generate images, and then we have a text plus image to image model. This paper is instruct pix to pix that tries to find differences between images. So the way this paper works is you have an image and you provide a modification text, and then you obtain a modified image incorporating that. So we try to do the same style transfer using our method. In generator, we provide the pair of the image and the text, and then it tries to generate the modified or it tries to rewrite the prompt so that the generated difference image is the best. So over here we use gram matrix distance. This is the metric used in style transfer learning, where the gram matrix come from like the first few layers of the VGD network, and researchers have found that this is the best representation of style transfer. So we use this as a scorer, and then we do the same process of prompt rewriting, and then we again do the iterative process, and we do this until convergence or for n steps. And our method can do image editing, style transfer. Over here, you see various different styles for a given Mona Lisa painting. And on the right side, we see the outputs incorporating these styles. So in the first, we see a crayon painting, so the output corresponds to that. The second one has a blurry effect, and that is captured here. The third one is a fine-grained artistic carpet style, and that is again captured in the third row. Again, to recap, all of it is done just without any sort of training. There's no training involved in this work. We use strong LLMs and corresponding scorers in the respective modality. And now we also see how the performance vary over steps. Naturally we do iterative, and we want the performance to improve with respect to step. So we show the optimization matrix that is the scorer output, the clip similarity, and the pick score, and the downstream matrix spice. And then both of them improves as the steps improve. So with improving step, the captioning improves. And yeah, I think after 10 step, it kind of saturates. So we stop at 10 steps. The same is observed in improved image generation. We see an upward trend in both pick score and human evaluation. We do human evaluation at like 0th step and 10th step and then 20th step. Yeah. So the performance improves here as well. And lastly, I want to show like a fun application enabled by inversion of multimodal models into the text space. So what we do is we have an input image like this, and an audio where the birds are chirping. So we want to do some sort of arithmetic where we are adding these two things into a resulting image. So the way it happens is we use our mills to caption this image. So this image is captioned using our method, and then the audio is also captioned using our method. And wait, yeah. And then what we do is we then add both of them using a text prompt, and that results in an image as shown here. And we do the same with multiple examples. So yeah, to recap, we have like an image that has a stop sign and a sound capturing the thunderstorm. So then the resulting image tries to combine these two different things from two different modalities. So yeah, this is the end of the presentation. Please refer to the paper for quantitative results. We do not include quantitative results here, but we show for all the tasks we show. Sorry, for all the tasks we show improvement across uh, state-of-the-art methods in respective domains that does not use any training data. Yeah, so this was my talk, and yeah, we have plenty of time for discussion and questions.
So for the first row, what was the input audio there?
The input audio is that of birds chirping.
Okay.
So that's what is being tried to capture here. The birds are here, and this image kind of gives the sensation that the birds would be chirping in this image. So that's the overall idea of cross-modal arithmetic.
Yeah. So it's kind of the multimodal kind of arithmetic takes clues from the audio and diffuses it. So like for the diffusion models, I think so you used two state-of-the-art models. One was Snell, Flux Snell, and the other was so
And
was there any reason to like use those two, or did you randomly select those?
yeah, these are I think the best performing. I think when we did this, Flux and Stable Diffusion 3. So these two are like the best, were the best available method at that stage. One thing to note here is that some of these recent models, they try to already incorporate this prompt rewriting. So to have like a fair comparison, we do not choose a model that has these prompt rewrites. So we wanted to make sure the generation is directly doing the generation is being done from the input prompt and not an updated version of the input prompt, because then it's very difficult to compare how good the rewrite is. Yeah.
Yeah, the generator is Llama 3, and the scorer is that 3.18, and the scorer is Metaclip that you have used here, right?
For improved image generation, the scorer is PicsScore.
Okay.
For image captioning, Clip is the score, because we want the generated images to be liked by humans, and PicsScore correlates human likeness with its score, with its value. So we use this as a score to improve how good the image looks.
True. Plus, like if we look at the scalability factor, so uh, MILS relies heavily on the generator and the scorer modules. So I would like to ask is how does the MILS perform when applied to tasks or modalities when the scorer is less effective or unavailable?
Yeah, that's a question. That's a good question. Uh, f- uh, yeah, so overall, it relies on the fact on how good the scorer is. So if the scorer is too weak, then the performance will not be good. But at the same time, if the scorer is weak, even those models that are being trained using these data sets will be weaker. Because ultimately, all these VLMs kind of are trained with like this scorer kind of thing. Like for example, if you look at any of the VLM that has image captioning, their encoder will still be something like a clip encoder. So all those models also rely on how strong the scorers are. So rather than using these capabilities of scorer at train time, we use it at test time. So yeah, definitely the performance would be lower if the scorer is not good, but at the same time, all the other models will also suffer.
Cool, cool. Yeah, that's true. So for scaling up to multimodal tasks, complex multimodal tasks, like if you look at the application area of 3D spatial reasoning or like real-time multimodal interaction, do you see this framework scaling up to that?
Yeah, yeah. I think yeah. I think this was this came up even previously in our discussions.
Mhm.
The spatial reasoning part can be done if we have a scorer that tries to find like the segmentation or all these methods. Like if you want to do spatial segmentation,
Mhm.
then if you have a scorer that can do that, then I think yeah, this method can easily be extended there. But yeah, obviously the trade one consideration there would be how fast it is, because then we need to do multiple iterations. So if the scorer is too slow, then I think that becomes a bottleneck. So if we have a fast segmentation method or any fast scorer, then I think this model can be directly used.
Yeah.
Yeah.
Plus, like, uh, I don't think so. This research is like focused on the op, like uh, the deployment specific or like taking this directly into production. I think so. There might be some optimizations that need to be performed. So, have you kind of looked at something to make those loops faster, like delving into CUDA or stuff, or like it's still raw
Uh,
from that end?
yeah, we did not investigate that,
Uh-huh.
but but I think the argument is if you have any specific application in mind,
Uh-huh.
for example, if you only want to do image captioning, then I
Mhm.
think the better way is to train a model for image captioning.
Yeah.
So we see our method more as like a debugging tool where you would want to invert some generator or scorer and see the capabilities and perturb that. So so it's more like it's not like a deployed tool where you want to see how good the image captioning is, but rather more like if you have like a new task in mind and you have a scorer, but you don't have a generator or you don't have enough data to train for it, then you can leverage the power of scorer to invert the capabilities there. So we
Mhm.
see yeah, applications there, but I think in cases where we have large amount of paired data, like for example in image captioning, you have plenty of data. So over there, we don't see this as being like applied. This is more like trying to see the capabilities of scorer by inverting it.
Mhm.
And so this is the intended, I think, target. So that's why we didn't try further optimizing the speed of the loop and so on.
Mhm. Yeah. Yeah. Another question will be like I had this prepared beforehand. So there was a query with respect to comparing with the gradient-based space methods. So, like you might have heard about zero cap, the
Yeah.
gradient-based method C zero cap that has been used for some similar tasks. So, what are the specific trade-offs like and the comparisons between the MILS gradient-free approaches and the gradient-based space methods in terms of accuracy, efficiency, and flexibility? Like,
Yeah. Yeah, that's again a good question. So,
uh,
what we observed was all the other method like zero cap you mentioned, and also Mia cap. There are
mhm,
few method that tries to do something like a memory based retrieval. So the idea over there is if you have an image and you want to caption it, you first have like a memory bank, and then you just find similarity, and then you find the closest caption, and then you find the closest caption, and then you score that. So the overall idea looks somewhat similar, but then the most important difference is the generalizability there. So most of these work they try to have some structure in the sentence formation or the caption, and because of which it does reasonably good in image captioning, but it doesn't scale to other tasks like improved image generation or style transfer or even cross-model arithmetic that we showed. So
mhm,
all in all, our method is more uh, generalizable and plug and play, whereas that method, all those memory-based method, they have some structure that they try to exploit. So first of all, they are specific to image captioning. And another interesting thing that we observed was we had an experiment where we tried to caption imaginary images. So we generated first an image saying an astronaut in space and something like that, and then we asked both the methods to caption. We observed that our method is able to better capture that because the generator is able to do these imaginative uh, caption generation. Whereas if you have a memory bank and you try to retrieve, typically those memory banks only contain real world captions or like captions that actually corresponds to images or come or it comes from some predefined data sets like Coco and so on. So they struggle to generate captions for those imaginary images. So I think these two differences, I think, stand out.
Yeah, yeah. Think so. Uh, uh, like in some scenarios, one will be better, and in the some other scenarios, like this will be better. So like we have to quote that we might have to probe, and based on the previous researches that have been done. So on the downstream task, so we might select one that's ideal for yeah use
Yeah,
case. Mhm.
yeah. In some way, yes. But also like ours is like pretty generalizable. So if you have a
Mhm.
scorer, it's pretty much guaranteed that you will be able to see this loop working.
Yeah, true. Another query was about the initial candidate set. So, in on the page number 7 under the cross model arithmetic or the elevations in section 4.7, you had
Yeah,
you had a, a statement about the initial candidate set, which is critical for bootstrapping MILS. So,
yeah,
like there's a line that says that with respect to initial bootstrapping set is critical to ensure that the generator can produce sufficiently diverse candidates and avoid local minimas. So,
yeah.
how does that quality and diversity of the set impact the final output? I mean, in that some subsample, yeah.
Yeah, I think it does pretty much. Let me maybe try to open the paper and we'll see some. Yeah, I think that it helps in the diversity. So if we
Hmm.
do a very small initial set size, then the performance is lower because it is not able to find a lot of uh, good scores. Initial set size, I think.
It's on page number 7.
Yeah,
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 page.
yeah. I wanted to show
Just
this.
above. Yeah,
Yeah.
okay. Hmm.
So on the right, we see this plot of initial set size versus performance. We start with 30, then 300, then 3,000, then 30,000 initial set size. And we
Hmm.
see that the performance improves quite a bit in this scale.
Hmm.
So the reason for that is if you only give, say, like 5 captions and say, oh, then score this, and the 5 caption may talk about, say, something in a park, um, but the image that you have might be of a cat. So
Hmm.
then, even though the scorer will score all of these, all the scores will be low. So then, there's not a lot of thing to guide the generator to generate more pairs
Hmm.
or to generate more samples. So the bigger the initial set size is, the better it is in terms of the scorer being able to find uh, a reasonably correct caption. So the bigger the set size is, the more likely it is to find something like that.
Hmm.
Yeah.
Cool. Uh, Next, I would like to ask about uh, like uh, if from a future perspective, like if you look at the MIL is being applied to emerging modalities like haptics or augmented reality. Uh, how would you envision this kind of future?
Yeah, in fact, I feel it's very promising, and in fact more promising than other fine-tuning methods.
Mhm,
So naturally, that's what we also saw in like the video image and the video research,
mhm,
that the understanding model develops first and then followed by generation models. For example, we had clip before we had stable diffusion, image generation, and so on. And similarly, we have video clip and video understanding before. Now we are starting to generate videos. So
mhm,
even for something like haptics, we will have understanding models first. So the good thing is we can use those understanding models as scorers in this work, and then use we can use scorers, and then we can use LLMs as generators and these haptic models as scorers to reason about the model themselves. So I feel, yeah, it has good applications, especially in domains where we have lesser data.
hmm. True, true. Uh, Another query was with respect to the cross-modal arithmetic. So you showed some interesting applications there, but I wanted to know about how do you ensure kind of the semantic coherence uh, when combining modalities that are vastly different here, like audio and text.
Yeah, yeah. I think the clear answer is that it depends on how good the text can represent something. I'll show a
Mhm,
good failure case here. Uh, okay, I think I have it in the slides here. So if you look at the last row here,
mhm,
it is able to capture the fact that it is a carpet and the carpet design, but it could not capture the exact pattern because we are transforming everything into text modality. So it is very difficult to describe this thing in text and hope to reconstruct it. So this, I would say, is a failure case where it's not a failure case, but rather like a limitation of uh, trying to represent things as text. And that is,
mhm,
I think, where vision modality is better than text. So yeah, we were not able to, the text was not able to capture, and hence the style transfer here. So this is where I see the limitation being. But if you are able to somehow represent this shape like this, for example, better in
mhm,
text, then I think we'll be able to again overcome this limitation. Yeah.
mhm. Cool, cool. Thanks. That was all the questions from my end that I had prepared and I came up with.
Yeah.
Uh, Thanks for the awesome talk and taking time out to present such a.
Yeah. Are there other questions in the audience, or are we done?
Um, I had a question about the style transfer itself. I
Yeah.
know I read in the paper that it's limited by the resolution of the gram matrix distance.
Yeah.
So I was wondering in the future, how would you see, the style transfer being improved by this method?
Yeah. Yeah. My limited experiments with this style transfer, I feel gram matrix might not be like the most accurate metric here.
Mhm,
So maybe there needs to be some advancement in the metric itself. Yeah, once I think if we have better scorers, the style transfer would further improve. Yeah, I think that was the limitation, and the other limitation that I discussed was the limitation in terms of trying to express things in text, and like as in the last row, we couldn't express this pattern better in text. So if we find some better ways to represent this in text or some different representation, I think that would be helpful in learning this.
Thanks, that was really helpful. I was wondering, what in terms of like taking this research forward, what are the ways you are exploring? What do you see as the future of this paper and this research and developing it further?
Yeah, one obvious direction would be trying to add like different tasks. Like I think that's what Mayank also mentioned, the spatial aspect of it. Like if you can you try to add like some spatial 2D reasoning or have something like this. And the other that we have discussed in this chat is how can we extend this to data scarce domains. That I see being really helpful. From the speed perspective, yeah, right now I feel the because it has many loops, the inference is somewhat slow. But yeah, there can be efforts to improve that, but I don't see that as being like major because that's not, I think, the intended contribution of this work.
Mhm.
So yeah, I think maybe extending it to different domains, data scarce areas, and yeah, I think that's these are the possible future directions.
Thank you. Thank you. That sounds great. Good luck with the future work on this.
Yeah, thank you.
Hello, Ashutosh.
Yeah, hi.
Yeah, really great work. I had a few questions here. In the initial figure, if we see the generator and the scorer image, is it since the scorer is the heavy model here, we really want the scorer to be the state of the art. Are we enhancing generator or are we enhancing scorer in this here? This part?
Actually, both of them are important. So even if the scorer is perfect, but if the generator is not able to generate diverse and good captions or like good candidates,
Mhm.
then the overall loop will not be effective. So we need both of them to be good. And that's what we also show in the experiment, I think. So being the supplementary that both of these things matter. We modify, yeah, we have ablation on the type of scorer and also the number of parameters of the scorer, I believe. Where is it? Yeah, it's here. So if you improve the model parameters, the scorer, so the performance improve both by improving the number of parameters in the generator as well as the scorer.
I
So
see.
both of them are important.
But the most causal learning part is coming from the scorer side, right? Because I have a vision model there. They
Yeah.
hope to
Scorer is
ensure
the
you're learning the causal thing in Scorer. And
yeah.
say in the image captioning case, you're kind of rephrasing the output captions using an LLM.
Yes.
So
Yeah.
do we call that LLM enhanced knowledge, or because like I'm just using my multimodal at the end of the day? I'm not, I'm not encoding my image as some different textual characters using LLM to get generate an image.
Yeah.
So it's still the VLM doing the most of the important part.
So, I mean, by VLM, we mean generally where the image is being fed to the LLMS tokens or something. So, this does not use VLM. So this is kind of like an alternative to VLM. But yeah, you are correct that this is a pure LLM based generator. There is
So even the scorer is LLM?
no, the scorer is like these clip models or like
Yeah.
these.
So they're ideally, they're capturing the image part, right?
Yes. Yeah,
So
they're capturing the image part.
ideally, we are not sending it as a text token to an LLM. So it's not like
Yeah.
we are enhancing the knowledge of LLM or LLM learning any multimodal knowledge, but it's
Yeah.
improving the knowledge of a vision model or the other vision encoders present.
Yeah,
In,
but also, sorry to interrupt, but also this is kind of like the core contribution, right? That we don't want to train VLM or we don't want to feed images directly into the model because then that requires training. So I think that's what we are trying to avoid in this work.
I see. No, thank you.
Any more questions, folks? If not, we can end this call and thank Kumar Ashutosh for the awesome presentation. And yeah, best of luck for your ICML. So you're going there this year?
Yeah. Yes, in Vancouver. Yeah, in July.
Yeah. Yeah. Cool. Cool.
Okay.
Best of luck and have
Yeah,
a
thank you.
great ICML.
Yeah, thank you so much for inviting me.
Thank you
Thanks.
for the talk. Good luck.
Yeah, welcome.
Bye. Take care.